Hello everyone, welcome back to my channel, Black Box Engineering. I want to keep on making my LTSpice videos. This one's going to be focusing on how to set up sub-circuits, or there's actually kind of two methods here. One is a sub-circuit, one is called a Hierarchical Netlist circuit. I think sub-circuits are a little bit easier from what I remember. So the first thing I have to show you is make sure that you have your paths set up correctly. So if you go to your little control panel with the hammer here, and then you click on the sim and lib search paths, make sure that you have your folder where you're saving your stuff listed in both symbol search and library search. This has caused problems with my stuff before, so the way that you get the path address, if you're not super familiar with that, just go to your file explorer. Actually, hold on, and then you gotta just find where you had your stuff saved. Mine is on my desktop. And then I have it in LTSpice, and then you click this top thing, then you copy this into the top and bottom. So that's one important part of doing this. What I'm going to be modeling is a idealized version of an operational amplifier having two different circuits. It's similar to a manufacturer part number made by Analog Devices. It is a two circuit, technically it's an audio op amp. The part number is OP275GPZ. It has power, negative, and two different operational amplifiers inside of it. We're not going to really worry about the in-depth specifications. We're just trying to make an ideal setup rather than having to remake a bunch of let's say if you had a circuit where you had a lot of op amps, it's easier to just make little sub-circuits first and then place those blocks rather than having to put a million different little parts in. You'll see what I mean. So first thing we got to do is make our circuit. So what we want to do is go to our components, and then in the op amp little folder here, we want to find universal op amp 2. This is the one that I found works the best. So just give me a second here, and then oops, I gotta make sure to rotate this. And then I'm going to take this item and I'm going to copy it, but I'm going to rotate it, and that's Control E. You'll see why I'm doing it this way. It's a little bit quicker to match up the different signals here. Like the negative is going to be on the same line as the negative, even though positives are technically on the opposite sides. It doesn't really matter that much here. So then what we're going to do is terminate a bunch of wires together. You do that is, again, if you hit F3, draw a wire somewhere, and then click on a endpoint, then hit escape. You can terminate a wire anywhere. And then we need to hook up the other positive as a node. I'm gonna need a little bit more wire length, so I'm just gonna redraw a couple things here. So now that we have these lines where we want them, we need the outputs as well, so let's just bring them to the same level here. and then the inputs are going to be their own lines. We do not want to tie the positives and negatives together. We want them to be separate circuits. So the way I usually do it is I bring them off to the side like this. So basically this is our reference circuit, and then what we have to do is add label nets or node names to these things. So we're gonna call the left one out A. We're gonna make an output, so that's out A. We're going to call the other one out B. And then we also need voltage supply and our inputs named as well. So we're going to say V plus and V minus for the common voltage here. So V plus, let's just call it an input, even though technically it's, I guess you could consider it a bidirectional, but typically it's polarized for these kinds of things. So, and then I'm going to call the negative shared leg as V negative. That's pretty typical in like data sheets. And then the way that data sheets usually label their inputs are negative and positive in A, negative and positive in B. So negative in A, could be an input. You can right click these to change them. So and then this is the positive in B, in A. And this is positive in B. Okay, so it should look something like this. I mean, technically the inputs and outputs don't really matter, but it's just kind of nice to keep it consistent with what we expect. We know that voltage source is typically an input, and of course on the other side of the op amp is always an output, so that's why I've labeled them the way that they are. And now we have to save this as some unique name. So I'm going to say file save as, and I don't have this in my particular folder right now, so I'm going to call it OP275. in my LTSpice directory. The first method I'm going to go through is going to be the library netlist version. It's a little bit more in-depth, but bear with me here. It's just a little bit more steps. I might actually split these into 2 different videos because I don't want to drag on too long on the whole thing. So anyway, first thing we have to do, if you want it as a netlist rather than a sub-circuit, what you want to do is click View, and then click the Spice netlist here, and then you want to copy this, and typically you want to use like Notepad++, because Notepad doesn't save things properly, so I'm not going to download anything new. And then you want to paste this into here. I guess you couldn't use Notepad, but I like Notepad++ a little bit better. You're going to want to add a couple of different lines here. So right at the beginning, you want to do dot subct, and then we're going to say OPZ275 because that's what we named it. And then we got to list the same names of what we did for the pins. So we got to use these same names. Let's see if I can get a split screen going on here. Okay, OPZ27. Did I say it? Hold on. No, I said OP275. It would not work if it's not the same. So, anyway, so it doesn't really matter which way you list these as long as they're the same. But netlist order does matter here. So, like for example, out A would be the first netlist item. Negative in A is going to be the second netlist item. Positive in A is going to be the third, and then so on. So I'm just going to keep on writing these in. And V positive. And the reason that I wrote it this way, I believe this ends up being like a typical setup of a 4-circuit op-amp. Let me just show you a datasheet as an example. Hold on. And this is the circuit that we're referencing. So it's open source. So yeah, I just followed the same netlist order. So, and typically when you count like pins, it's going to be 1 top left, 2, 3, 4, and then it wraps around the bottom 5, 6, 7, 8. So I basically just matched the same relative flow to kind of make it consistent with data sheets. It's a little bit easier for me to go that way. So the next thing that we need here after back NO, we also need dot ends OP275. I found out the hard way trying to make like a netlist version. It took me a lot of researching to find out why my circuit wouldn't run. It's because it was missing these, and I'm not really sure why the well, I mean, I guess okay, so LTSpice doesn't know that we're making a sub-circuit, so I guess it makes sense as to why we're adding these. As for this, I don't know why .n doesn't work for both, but it's just important to add that. But anyway, so now this could be saved as 2 different things. You could either save it as .lib file or a .sub. It does not matter because they act the same way. So I'm going to save it in my LTSpice folder as a. I'm going to save it as a .lib, I guess. It doesn't. Again, it doesn't matter. But where's my? I like to use the same name, so op275.lib. Okay. So then we have to make a new symbol for this particular subcircuit. We can close this now because that doesn't matter. So on this same page, we want to do File, New Symbol, and then we got to add some details to this. We do have to add the pin names in the same order as the lib file in this particular example. So you'll see what I mean real quick. So the way that you add pins is, I think it's I don't remember the shortcut, but you can just right click and add them, and they have to be the same name too. See how the netlist order says 1, and then the way that this is sort of backwards, but pin label, if I hit left, it'll look like it's justified to the right, but that's because we're just leaving space for text inside a box. You'll see when I actually draw a bounding box for this as to why this makes sense. And then we just keep on adding pins. So right click, add pin, negative in A, netlist 2. Oops. Negative in A. Make sure that you actually click some kind of justification, otherwise the text will not be visible. Netlist 2. I'm going to put it at least one space between, because if I put it like right here, it's too squished together. So, and then you just gotta keep on adding pins in order. So plus, oops, plus in A, add pin, V negative, left, and then on the other side we just keep on continuing. And it's totally fine to switch like spacing up if you don't have room for things. And this time we're going to use the right justification. So I have no clue on how much space we'll have, so I'll just estimate this as the right side of the box here. The next one is negative in B. If I can, okay, so that's too close. I'm gonna move these out one more dot over, so add pin, out B, and then finally V plus as the last one. Dang it, I keep on. So this is like our setup as our integrated circuit, if you can think of it that way. The shortcut is pressing R, and I like to just give it a little bit of space, top and bottom, and I like to align it with the grid, kind of like this. And then just save this as the same name as the circuit, so File, Save As. I'm going to do op275.asy because that's the symbol file extension name. Okay, to use this, we need to add symbol attributes. So on this, on the symbol tab, we need to do Control A, set it to cell type, CELL, and then we're going to make the prefix X, and then the value, this one right here, we're going to have it the same name as the circuit, OP275, and I just use X because LTSpice doesn't know any other value when you're setting up these cells, so X is like a default for something unknown. And then we're going to hit OK, and it'll turn yellow. We want to hit save, Control S again. So if we want to use this circuit, now let's just go to like a new schematic here. If we hit the little thing here, and then switch folders to LTSpice, we should see OP275 listed here. So we want to hit OK on that and place it somewhere. But the thing is with hierarchy ones, it won't just work out of the box. Again, I found this out through trial and error. A lot of forums online answer this. You gotta add a spice directive. Two ways to access that is you can add this .op thing, or you can just type S. So To make this work, you gotta type .lib, hit OK, place it somewhere in here, right click this, and then what we want to do is click browse, and in the same folder we want to direct it to the .lib file that we made earlier. So let me just find that here. It's gonna say LTSpice Netlist in the oh wait, no, sorry, not Netlist, lib file. It has to say lib file, and then hit open, and then hit OK. So if you don't have this with the hierarchy like method, so if I try to run this, it would actually throw in, I know there's no voltage or anything, but so if I hit, I don't know, 5 seconds and hit OK, it says unknown subcircuit called in blah 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 blah, because it does not know, even though we have like a subcircuit tied to this and whatnot. We've got a symbol and everything. It doesn't know the like the circuitry in it without the lib file. It's like it's referring a null like circuit. So that's why we need that spice command. So again, I'm gonna just add it again, .lib, if I can spell it right, .lib, right click it again, browse, it probably will give us another error. No, actually it didn't. So so we saw that it ran. It's not going to actually give us any like values because there's nothing hooked up to it. So in essence, the netlist or the .lib file is referencing this circuit but in code. That's literally what we saw in the weird looking text. If we were to look at that again, so let's just go back here a second. Yeah, if we look at this, again, we added this line, but we're just saying, hey, we're starting a subcircuit here. We're going to call it OP275, and here are the pin outputs, the pin names in netlist order. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and then again in the same order because it matches. Like 1 is out A, 2 is negative in A, 3 is plus in A, and then following the same pattern as the actual like data sheets that we're trying to reference to. And then these codes are generated automatically when you start drawing things. It just tells you because this is what Spice is. It's just code to make a circuit simulation actually work. It's kind of in the background. Most of this stuff doesn't matter to us so much. When we draw a circuit, this stuff is happening in the background. I think in the old days, if I remember right, I think you only had the code and you'd have to set up like weird things to get like any kind of visual output, stuff like that. It's advanced into a mostly streamlined process. So again, this is not the easiest method of doing a subcircuit, but it is one of two methods. So the reason that you would have like this setup, a lib file technically takes up a little bit less space than an actual like if you were to do the subcircuit method without the netlist code stuff. It also like if certain parameters don't transfer nicely using the other method, it might be only possible to do it in this method. I haven't seen or heard of a situation where you would have to use this method. I actually don't really prefer the hierarchy method that much, because you have to do more steps to get it working. But either way, it works properly. So let me just show that really quick here. Let me just close these windows, and this is just like an example, like real quick. So if we do voltage and just set it at 0.1, this is gonna just be like a quick, like, positive negative gain example. So let's say we want 100 ohm resistor here, and then 1000 ohm resistor here. We're gonna, oops, I hooked this up wrong. Hold on. Oh, I see. My 100 ohm resistor was not in the right spot. So I'm going to hook this up into the negative side, and I'm going to branch off of here to match up with the 1K resistor, and then come over here into the output. I'm going to label this as I guess voltage output A. If I can click in the right spots. And then we're gonna add a ground. Okay, so we've got that side. We also have to have power, so I'm going to add a positive and negative power. I'm going to use my personal trick. To make a split voltage. I don't know, let's say 5 volts. So we need positive power, we need negative power, oops, yeah, a goof there. It would be both positive. That would not be good. So that negative goes to negative, positive goes to positive. And then on the other side, let's say we wanted a non-inverting amplifier. The way that you set that up is we have our output. Let's go to a 1K resistor. I keep on clicking the wrong spot. VOB. Then we need another like input like signal. Think of the V1 and V2, or I guess in this case V4, as the input signal that's coming in. So we just want to share grounds with these, and then we need to go from the positive output to the positive side of the other op amp here, and then we need a 1K ohm This is where I kind of screwed up with my spacing a little bit, but let's just move some things around so it looks a little bit nicer. And I'm gonna change the position of the negative voltage real quick. Hold on. Sorry. It's just trying to make it as neat as I possibly can, but I'm gonna end up with weird looking lines here anyway, so oops, that didn't line up properly. So we've got our input signal coming to positive in B, our negative gain, our negative input is tied to 1K output and to ground. It's the opposite setup as this. We also need to have the negative power go somewhere, so I mean voltage, I guess. So probably not the nicest looking thing, but and then the way that I tested these is I made this a sweep. So in this case I literally just, instead of sweeping both voltages at the same time, because when you do a sweep, it steps them differently. So I'm going to change the transient into DC sweep, and we're not going to use second source and third source, but we're just going to use like one source at a time. V1, which would be the inverted amplifier. Let's say we want to start at 0, stop at 5 volts. I guess I don't really need an increment. It'll still run, so anyway, so if I probe the output, oh, I have to hit run again. So we see that the input voltage is going linear from 0 to 5, but if we look at the output, it'll do its amplification up to 5 versus the input here. So yeah, the input increases slowly, but within half a volt it already reaches 5 volts on the output, which is what you expect. But in this case it doesn't go positive because this is an inverting amplifier, so it's going from 0 to negative 5 volts. So yeah, kind of a fun thing. The other example is going to be, well, let's change this up a little bit. Negative 6 volts. There. Yeah, so this is a way to kind of visualize how inverting and non-inverting amplifiers work. And this is just like one method of doing like a sub-circuit. It could be, I mean, yeah, this is kind of messy, and it does take a little bit more steps to get to this spot. But it might be nice to not have, like, because with the other method you have to have circuits made beforehand in your library folder. So you'd have to have, hold on, let me just open it. You'd have to reference this as well. Technically speaking, I mean, it is referencing this, but not directly. It's literally just referring to the code at the .lib file. So yeah, kind of convenient in one way, but just a little bit more steps. The next method is going to be, in my opinion, the easier to understand method. So yeah, hope you enjoyed watching. I always like talking about this technical stuff. Oh, I'm sorry, I forgot to show you the non-inverting side. So if I change this really quick, instead of voltage 1, let's just ramp up voltage 4, because that's this one right here, from 0 to 5, and hit run again. Oh, wrong side. So this side, and then we see the opposite thing happen. So, and just go to 6. Oops, not 56. 6 volts. Not. So, yeah, this input voltage goes linear, but the amplifier boosts it way faster. And at 0.5 volts, the compared to, yeah, at 0.5 volts, it's already at 5 volts. In fact, it reaches an output of 5 volts at about just under 5. So yeah, so what would be the amplification factor on this anyway? 1000 divided by 100 is 10. Well, duh. Let's see, 0.5 times 10. Yep, that makes sense. So that's an amplification factor of 10. If I were to do 2K, it's going to go up to 20, and then it's going to ramp up even faster than that. And again, I hate that its auto tick calculation is not the best in the world either. That's another problem with LTSpice, in my opinion. Every time you hit run, it assumes what you want. So the horizontal is 246 millivolts. Let's see if that's right. Yeah, 246 millivolts. So 0.246 times 20 is approximately 5. Of course I'm not, because I don't have my cursor in the exact perfect spot. But anyway, the output's not even fully 5 volts because of some losses here and there. But yeah, cool way to do subcircuits. You can set up a whole lot more complex things. It's better to sometimes work with a group of like subcircuits so that you don't have to you don't have to over-engineer. Well, sorry, no. One, you don't have to reinvent the wheel. You can there's online communities and even like resources on analog.com to download subcircuits. In fact, they have their own list of subcircuits. That's what like all of these different things are technically. I don't know what it means. Oh, different kind of switches, like multiplexers. Those get really complicated. So yeah, so they have their own subcircuits, but this is how you make one, at least one method. So anyway, if you like the video, drop a like, comment, subscribe, and hope I'll see you in the next one. I'll explain the other method to make a subcircuit in the other videos. So have a good one.